With this problem, what we want to do is we want to find an in-behavior power function. What does that mean? All an in-behavior power function means is that we're going to take this function that we're looking at, reduce it all the way down, and look at the leading coefficients and the leading terms. And whatever those reduce to is what our power function is going to look like. With a power function, we're not interested at all, not interested in what's going on at 0, but we're interested in what's going on as x approaches positive infinity and negative infinity. So let's take a look at this guy. It's ready to go. It's already organized correctly. So what we want to do is we just want to see, will the top factor or bottom factor? And I don't think the top will factor. The bottom, I can pull out an x squared. So, you know, when I factor the bottom and look for factors in the top, I don't really see anything that's going to go away. So the next step that I'm going to take that is basically what my in-behavior is going to represent is going to be to look at these leading terms, the leading coefficient and those leading terms. And that's going to give me 6x squared over x cubed. So since nothing factored out of the entire function first, what I'm going to do is reduce these guys. And when I look at these guys, I notice that all my x squareds on the top are going to go away, and my x cubed on the bottom becomes x. And so if you graph 6x squared plus x minus 1 over x cubed minus 7x squared, when you look at values that are really, really, really large, you're going to end up with a function, an in-behavior model that looks like this. Y equals 6 over x. With this problem, we've got a piecewise function, and with this piecewise function, what we want to do is we want to look at the limit in a couple of different places and just see what's going on. So the most important thing with this is to be able to graph it correctly. So here's a graph of what that limit looks like. And remember, the point 0 is actually going to be included right here. We're including this point right here. Okay? So the question then for part A is, as x goes to negative infinity, what are we approaching? Well, that's this direction. And so as you go towards negative infinity, this graph actually is going to start approaching 0. And if you were to zoom way out on your, or I'm sorry, not 0, but 1. If you were to zoom way out on your graph, it's going to end up looking like a 1. And how can you tell? What's an easy way to tell? Look at the ratio of those terms. That will always tell you, the ratio of the leading terms will always tell you what your in-behavior model is. And in this case, our in-behavior model is the line y equals 1. Okay? Part B then says, what about as x approaches positive infinity? And again, as x approaches positive infinity, let's change up inks here. As x approaches positive infinity, we're going this way. And as we go this way, our graph is going to approach 0. Remember, in this case, we're getting really, really big numbers in the denominator, and the top, the numerator, never changes. Since the numerator never changes, that fraction gets smaller. Since the fraction gets smaller, we get close to but don't touch 0. Next, we want to look at part C, and it says as we approach 0 from the left. Well, anytime you look for a limit, one of the things that's really, really super convenient to do is to always check the value that you're interested in your function. So in this case, I have x minus 7 over x minus 3. I'm interested in this, and I want to know what's my limit when x gets close to 0. Well, take the 0 and put him in for x. And as long as we don't get an undefined statement, that is what our limit will be. So when I do this, I end up with negative 7 over negative 3. And that is my limit as x approaches 0 from the left of f of x. Well, the last guy, what about the last guy here? The limit as x approaches 0 from the right. So part D, the limit as x approaches 0 from the right. You'll notice there's a gap right here. So we're going to move towards 0 from the right-hand side, we're going to track the line, and this is going up, 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 up towards infinity. All right, we're going to look at this guy, and we want to know all the places where this guy is continuous. In other words, we want to know where we can draw this graph without lifting up our pencil, to hop over something, to jump to something, to draw an asymptote. And the easiest way to look for where some points of discontinuity might be is to just look at the graph. And on this function, we'll notice that if we look at this graph, we've got two vertical asymptotes right here. And what do we know about vertical asymptotes? Well, we know that vertical asymptotes occur where there's a 0 in the denominator. So let's take our denominator and factor it. And anytime you factor your denominator, the thing that you want to check right off the bat is, will it divide out or cancel out anything in the numerator? And in this case, I've got an x plus 4 in the numerator. My denominator is x minus 3, x minus 1. So all of those are different. Well, my continuity is determined by the denominator. This is in the denominator. This is where my continuity is determined. So I'm going to take x minus 3 and set it equal to 0. I'm going to take x minus 1 and set it equal to 0. And I'm going to look at these guys and find out what values of x give me zeros. And in this case, it's 3 and 1. So where am I continuous? I'm continuous from negative infinity all the way up to, but not including 1. I'm continuous from 1, not including 1, all the way up to 3, but not including 3. And I'm continuous from 3, but not including 3, all the way to infinity. And just a real quick side note, whenever you are using infinity, infinity does not get a bracket. It is not included. There's no specific number for infinity. It's an idea of a really large number. And every number you think of that's bigger than mine, I can think of one that's bigger than yours. So it just keeps going. We can't include infinity. But there you go. There's how you find some discontinuity with your function.